Hi everybody, welcome. We are on lecture 4 today, and we're going to be building upon what we have already looked at, which is stress states and calculating our principal stresses if we know something about the stress state at a critical location on a part. And today we're just going to do an example problem. That's our lecture today. Because I gave a little bit of an example last time, but I didn't work through many of the calculations in detail. And I want to do that so that when you see, let's say, a problem on homework assignment, that you're feeling a little bit better about it. So I'm going to provide an example problem here. So let's say that the state of stress So the state of stress can be defined by this. We're actually going to have a situation of no normal stresses. So sigma x equals sigma y equals sigma z equals 0. And tau xy is going to be minus 75 megapascals. So we're going to put some real numbers in. Tau yz is going to be 65 megapascals, and tau zx is going to be minus 55 megapascals. So that's our starting point. And so if you want to flip back in your notes, you could draw these on the cube with the stresses, and you would notice that these stresses all sort of the same order of magnitude, but some of them have opposite directions, right? Which just means they're not pointing toward the direction of the positive axis, right? That's normal to the plane. Okay. So what do we want to do here? So first of all, let's say to find principal stresses. Principal normal stresses, that is. So I just wrote principal sigma. Direction cosines for the 3 principal stress directions. Okay. So I'm going to write direction cosines. And that is for sigma 1, sigma 2, sigma 3. And the maximum shear stress. If we can do this for any stress that we have on a component, then we can start applying failure criteria and determining if it's going to fail or what our factors of safety are and things like that. So this is still a little bit of a review from, let's say, a mechanical design class that you may have had before, but we're going to solve it using the generalized stress equation. And then this one is not going to be quite as simple as the prior example that we had. Okay. So let me go to the next slide. And we had a generalized stress equation. I'm going to rewrite it up here. So it was sigma 3 minus sigma cubed minus sigma squared. And then there was a long coefficient for that term. Well, relatively long. So I'm going to change colors and write it in red. So it's sigma x plus sigma y plus sigma z. In this case, we don't have any of those, so that's handy. So that second term is going to go away. And then we had a plus sigma, and then we had a different long coefficient. So I'm just going to write it out here, sigma x, sigma y. So it was these combinations of the normal stresses. Minus the square of each shear stress. So minus tau xy squared, minus tau xz squared, minus tau yz squared. And then we have our final term, right, which doesn't have any variable associated with it in terms of the sigma. And then we had sort of some different combinations here. So the first one is a product of all the normal forces, sigma x, sigma y, sigma z. Then we have a term of the combination, so plus 2 times all of the shear stresses, tau xy, tau yz, tau xz. And then we had some other combinations. So minus sigma x, tau yz squared, minus sigma y, tau xz squared, minus sigma z, tau xy squared. Okay. So this is our generalized equation. And then we are going to take these different long coefficients and give them a name, okay? Because they do not change from stress state to stress state, okay? So if we have solved for sigma 1, sigma 2, sigma 3, the principal stresses are not, these numbers stay the same in the equation. So the first one is on the top, and it's the coefficient for sigma squared, and that is the first invariant. So we're going to call it capital I1. Okay, so that's the definition for those first three terms, the sigma x plus sigma y plus sigma z. And then the second long term that we have is the second invariant, so we'll call it capital I2. And then the third one, capital I3. So now we don't have to write out all of these terms all the time, especially since we're going to start canceling a bunch of them. But we can write the generalized stress equation like this. Whoops. Bigger. So sigma cubed minus the first invariant I1 times sigma squared plus, oh, I got a wrong sign. This should be a minus on the third term there. Okay. So plus I2 times sigma minus I3 equals 0. So what we do is we take our stress state and then we plug those in and cross out the ones that can be neglected, and then we solve the cubic. Okay. So let's do that for the givens that we have. So all we have are shear stresses. So first I can go through and cross out all of the normal stresses. So I1 becomes 0, right? I1, because we have no normal stresses. Okay, so that term goes away. And then the second term, this second invariant, the first three terms go away, and then we have just the negative sum of the squares of the shear stresses. And then in the third invariant, our first term goes away, and then the final three go away. So then we have 2 times the product of all of the shear stresses. Okay, so that cuts it down quite a bit. So I2 is going to be equal to, if we plug our values in, so minus tau xy squared. I'm going to put in all the minuses just for good measure. So minus, and then tau xy is also negative, so negative 75 squared minus positive 65 squared minus negative 55 squared. Okay, if we put all those together, if we square a negative number, it becomes positive. So then we have 3 negative numbers all summing together. We get a value of minus 12,875. And that is in megapascals. Right. If all of our, megapascals squared. Keep that good. So if all of our shear stresses are in megapascals, we took the square of all of them, added it together. We have megapascals squared. And that makes sense if you go back up to the generalized equation, because that is times a normal stress, our sigma that we're going to be solving for. So each term in the generalized stress equation has the units of megapascals cubed. So that's what each term has to have overall. So our coefficient has megapascals squared times megapascals of the sigma, and we get to the cubed. So we have first invariant, second invariant. Now we need the third one. So I3 is going to be 2 times the product of all the shear stresses. So 2 times minus 75 times 65 times minus 55. And we will get 500, we get like a really high number, 536,250 megapascals. And we took the product of 3 shear stresses, so now we come up with megapascals cubed. Okay. So we could write out our generalized stress equation now of sigma 3. We have no, or sorry, I keep writing sigma 3, sigma cubed. Okay, we have no sigma squared term because everything canceled out. Plus, what was our, minus 12,875 times sigma. And then our last term is plus, is it a plus? Nope, it's a minus, because that's the generalized equation. So then we had our 536,250 equals 0. Okay. So this should be, yeah, pretty straightforward. And the class is not a class in remembering how to solve cubic equations. So I'm going to see if I can do this in real time. We'll see if this works. I'm going to pull up Wolfram Alpha, and we're just going to solve it that way, if I can get a web browser up. Okay. Unfortunately, I don't have a keyboard connected to this, so give me 1 second. Nope. Okay, sorry, hang on 1 second. Okay. There we go. So how many people have used Wolfram Alpha to do stuff? Okay. So a lot of people have, and so it can just solve what we want it to solve. So I'm going to type in solve. If I can. So roots. This is a cube root equation. We should get 3 things out. All right, and then we have, I'm going to use the variable x just so that I don't have to type anything crazy in with variables. There we go. X cubed minus, yes. Oh, okay. I will make sure it's up in just a moment. All right, I stopped the, I'm not sure how to get it up. I can do display on the PowerPoint. That's not what I want though. There's no extension here. I just look over here real quick. All right, we are going to do it like this. Okay, so this is what I typed in. So I just said solve roots, and then I typed in our equation. So I have x cubed minus the 12,000 something x minus those other things. And then I will show you what comes out. Okay. All right, so we get, sorry if that's kind of small. Yeah, it's very small. Okay, so I'll tell you the results. If you can see this, then it has the equation, as I've typed it in, and it gives us 3 roots. Okay, so I'll write them off to the side here. So our first one is the largest one. Okay. Sigma 1, which is going to be 130.3 megapascals. Right. That's sort of seeable, okay? Sigma 2 is whatever is a little bit lower than that. So the convention we have is sigma 1 is always greater than sigma 2, which is always greater than sigma 3. So sigma 2 is minus 53.6, and they're all in megapascals. And then sigma 3 is minus 76.7. Okay, so we get 1 positive, 2 negative. So what this means is that we had our cube that we are in x, y, and z, right? And in order to come up with the generalized stress equation, we cut it with an arbitrary plane. And so if we rotate that stress cube such that all of the shear stresses that are input go to 0, and we're only left with the normal stresses, these would be the normal stresses. So the cube rotates, and then each face would have these coming off of it. So sigma 1 would be in tension, 130. Sigma 2 and sigma 3 are both in compression. So on our stress cube that's rotated to the principal orientation now, we have 2 arrows coming out, tensile, and then the other faces have the arrows going in. So you can kind of visualize in your mind how that cube is going to squish and deform, okay? If you draw those arrows on there, okay? So this is kind of half the problem, and this is good. So we have these now, and we could move forward with maybe further analysis, solving for shear stresses. But we also want to know, basically, how did we have to rotate this cube in order to get these principal stresses, okay? And so we're going to go back and solve for these cosine vectors that are going to help us to do that for each of these principal stresses, okay? So for sigma 1 is equal to 130.3 megapascals. Right? We had a set of equations that had L, M, and N in all of them, and the other parts were coefficients. And so we have a system of equations, and so I'm going to write them down for the first situation that we had. So if you want to look back in your notes, you can do that. So sigma minus sigma x times L minus M times tau xy minus n times tau xz equals 0, minus L times tau xy plus m times our difference of normal stresses, sigma y, minus n tau yz equals 0. And then the third one, similar structure, tau xz minus m times, tau yz plus n times sigma minus sigma z equals 0. So that's our set of 3 equations. And then we also have the equation that we want to make these unit vectors. So L squared plus M squared plus N squared equal 1. And you might be looking at this and thinking, well, we just did, in order to solve the first problem, this was sort of like 2 lectures ago, we took away the coefficients and we said the determinant had to be equal to 0. So we can actually represent this in a matrix format as well. So if that makes you happier, you're welcome to write it like that. So if I plug in some of the numbers, the first term on the top left, right, this one here, this L times sigma minus sigma x, all we have is L and sigma, right, because sigma x, sigma y, sigma z are 0. So I'm just going to write 130.3, right? So we're going to draw up our matrix, and then we're going to have the matrix we multiply it by as L1, M1, N1, and then that'll equal 0. So all of our terms will kind of match up. So that's the first term. The second term on the top is this minus m times tau xy. So we just have to put in minus tau xy. Let me make sure I get this right. Our tau xy is minus 75. So then we put 75 here in the middle. Our tau xz is same as tau zx, is minus 55, and it's negative there, so we'll put in a positive 55. Okay. And then we'll do the same for the others. So we'll have 75, 130.3. That's the same for everything in the diagonal. We'll have a minus 65 here, minus 65, and a 55. So the matrix is symmetric, right? Just because of the way the system of equations worked out. And if we solve that without the unit vector constraint, like we don't care what L squared, M squared, N squared adds up to, then we'll come up with some vector. And what we have to do then is scale that vector, the LMN, let's say it's a vector in 3D, we'll scale it down such that all of them add up to be 1. And so that's the unique solution to this series of equations. So when we do that, we should get L1 is equal to, I'm just going to keep it to like 2 digits of precision here. L1 equal 0.58, M1 equal minus 0.61, and N1 equal minus 0.5455, let's say. Okay. All right, so now we have the rotation for the alpha, beta, and gamma, right? That tells us how the plane is oriented for our first principal stress of 130.3. So if you want to, you could go back and sort of draw that vector in 3D space and see what the plane is normal to that and sort of how it's oriented with the initial set of axes, right? So it's not critical for us to be able to visualize it, but I just wanted you to know how to do that if you want to play around with it later. And I suggest you go and just make sure that you can solve this linear system of equations and get some of the same answers, right? This may be a really good topic for the class discussion board, right? You go in and say, hey, I solved it like this, I got a weird answer, or I solved it like this and I got a different answer, and we can come up with some strategies that everyone in the class could use. So if we take this one step further, right, L1 is the cosine of alpha 1, so I'm just going to draw that here. So cosine alpha 1 is equal to that 0.58, so the first angle from the x-axis would be, let me write this down, about 55 degrees or 0.95 radians. Okay. So these, angles are very reasonable, right? It's a normal type value that we might get from something like that. One way that you can describe this kind of problem is that we are finding the eigenvalues of a matrix, and then we're finding the eigenvectors that go along with those. So the eigenvalues would be our principal stresses, and then the eigenvectors that go along with each principal stress value is this LMN. So you might hear that language in another class, or you may be familiar with that in a mathematical sense, and now you can apply it to mechanics problems like this. Okay, so that's for the first principal stress, the tensile stress, and we can do the same thing with the other principal stresses. So we can do sigma 2, and that was equal to minus 53.6 megapascals. All right, and I'm not going to write out all of the equations again, but this matrix, right, will have the same values for all of the shear stresses. So I'm going to write them out. So 75, 55, and then the corresponding values as well, and the like this. And then across the center of that matrix is basically our principal stress. So minus 53.6. And now we're on the second principal stress. So now we have L2, M2, N2 instead of the ones. Right? And if we solve for that solution, we get L2 equals 0.56. L3 equals minus 0.19. Oh, whoops, that should be M, not L. And it should be a 2. Okay, and then N2 equals 0.80. Okay. So these are all like very reasonable values right on a cosine plot. And then for sigma 3, it was minus 76.7. All right, so then we just follow the same procedure, and we put that in as the diagonals in that matrix. And so I'll just write the answers that we come up with. So L3, 0.59, M3, 0.77, N3, negative 0.23. Okay. So these, we don't need to visualize all of them. We just see that the answers are reasonable. So now let's go back and talk about how this might relate to shear stresses. Okay? And so in your prior classes, you learned about Moore's circle. And you sort of said, well, we might have sigma 1, sigma 2, sigma 3, but really we're going to approximate it as a 2D stress state. And so we're not going to really focus on all those three. But we could if we wanted to now, right? So we had on the x-axis, right, our first principal stress. Just erase that. Right, sigma 1 was 130.3 megapascals. So we can plot that far out on the x-axis because x-axis is the normal stress axis. We do not have our second principal stress or anything at 0. So we're not doing anything at 0 this time. But we do have our second principal stress here. So sigma 2 equals minus 53.6. And then our sigma 3, I need to draw that out here, is equal to minus 76.7. Okay. And those are all in megapascals. So we can draw our Moore's circles from here. Right? We can remember what we learned about we need the maximum shear stress. Right, so I'll take the farthest most leftmost point and the rightmost point. I can't draw a huge circle because it would go off my screen, but that's approximately a circle, right? And so if you recall, how do we calculate the shear stress from here? You can raise your hand. You can just say the answer right there. Say again? Yes, the radius, exactly. So based on what we learned of the stress equations before in prior classes, we just calculate the radius, and that is equal to the maximum shear stress because the y-axis is the shear stress axis, right? And so in order to get that, we have, if we always follow the convention of sigma 1's greater than sigma 2's greater than sigma 3, then this is always sigma 1 minus sigma 3 divided by 2. It's the average of the extreme points, which is also equal to the radius of the circle. And we can call this, if we want to, our first principal shear stress. Okay, so tau 1, because it's going to be the largest magnitude. And so if we come in here and do the values, it's kind of 130 plus 200 divided by 2. And so we get something like 103.5 megapascals. Okay. So that's helpful. So I said that's the maximum. You all know this, right? But we can also go in here and draw our other two little Mohr circles, right, that go like this, that fit inside the larger one, and each of those circles will have a radius, right? So that means we can calculate the other two principal shear stresses. So we can have tau 2, right, which is going to be the medium-sized circle, which is sigma 1 minus sigma 2 divided by 2. Right. And then correspondingly tau 3, which is sigma 2 minus sigma 3 divided by 2. So if we have our conventions and they're all holding, then we can calculate the values here, and they will be lower, right? We usually just throw these values out because when we do our failure criteria, we really only care about the maximum shear stress. But if we wanted to now draw our stress cube, and instead of rotating the cube such that we only had normal stresses, we can rotate it such that we have a maximum shear stress, right, of this. And that can help us determine, future things for our failure criterion. Going along with these shear stress is the direction that you would rotate the cube in order to get these principal shear stresses, right? And if you think back to the Mohr's circle and where it comes from, let me just make sure what I have on the next slide. Yeah. We had, if you're talking about 2D, then you have your little stress square, right? And then you can calculate the principal stresses and rotate it. And if you, let's say you rotate it slightly like this to get the maximum normal stresses, well, we know that the shear stresses occur at 45 degrees to that, okay? And that comes from sort of this math, but then it also comes from those tensile tests where you pull on a ductile metal and it always fails at 45 degrees, right? And so we could say that then if we rotate this 45 more degrees, we'll be at one of the principal shear planes. If we rotate it minus 45, we'll be at another one. Okay. So for every rotation to get the normal stress, the principal normal stresses, there are two shear stress planes that could be a maximum, right? Minus 45 plus 45, which correspond to like minus and plus 90 on the Mohr circle. So so that same thing happens in 3D. Okay, so it's not a huge, it's not something that you need to really remember, but if you want to, you can look in the textbook and it'll show you for like, sigma 1 and sigma 3, how are the two principal shear planes oriented, and then for also sigma 2, for tau 2 and tau 3. Okay. So that is how to sort of fully describe the stress state. When I assign problem sets, which will probably be this week, feel free to use computational tools, okay? So I'm not testing you on your ability to hand solve the roots of a cubic equation. So use a solver tool of your liking, okay? What I will ask is I may add some follow-on questions to the problem set where I ask you what something means, right? What is the magnitude of this compared to the magnitude of this? What does it mean? so that you're not just like copy pasting from the solver and putting it in. You actually have to think about and interpret the answer a little bit. Okay. So I got through all of that exceedingly quickly today. And so that's all I have as far as lecture goes. Are there questions that have come up while you're starting to think about these things, specifically this example problem? No? Okay. So I will come up with some problems as we get started in the class. They'll have to do with just what is elasticity, and then thinking about calculating the principal stresses and the directions, principal directions for various stress states. So thanks everybody, and I will talk to you in lecture 5.